what he was working on doing was measuring accurately the carbon dioxide concentrations in the air. He had been a postdoc at Caltech before he came here, and when he was at Caltech, that's when he started measuring carbon dioxide. And he developed a method there that was new at the time, was very simple, and it took advantage of a newly available commercial product, which was liquid nitrogen. And so it was simple. You take an air sample, first you get rid of the water by freeze drying it out. You pass the air through a glass tube that's cooled down to dry ice temperatures, and that'll pretty much take the water out. And then you take that dry air, you introduce it into a known volume, you measure the pressure and temperature, so you get the number of moles. Then you pump away the air to freeze out the CO2 on liquid nitrogen, which was newly commercially available. And then you measure in a smaller volume the pressure, temperature, and volume of that smaller. You get moles divided by moles, you get DEM. And he was doing that on glass flasks he gathered at different places, and was able to show that the carbon dioxide concentration, although it was variable when you were in forests and things, was actually quite constant once you got out of that row. And so he realized, hey, to measure the change in atmospheric CO2, the key is to go to a good site. Go to a site where you're in this background. You don't have to wait. He was finding that in the afternoon he was always getting this constant value because the air was mixing. If you went to a place like Mauna Loa, you'd get a better number. But he also knew that this method that he developed, this liquid nitrogen manometry, wouldn't scale up to allow you to do a lot of measurements. And there was a lot of interest then coming from Roger about Scripps for launching this big program. So my father was brought here to run a program to measure carbon dioxide using the methods that he developed there with liquid nitrogen, but also adding another element, which is using an infrared analyzer to scale up the measurements. And one of the early area infrared analyzers in that box there. And let me talk first about the manometer. The way that so this was not the manometer at Caltech. This was a much more carefully engineered manometer that he built in the first few years he was here, starting about 1958. So this is the basis for us knowing that the carbon dioxide concentration in the atmosphere really was around 310 parts per million back when he started measuring. So this is designed to give you an absolute number, 310 parts per million. That guy over there only tells you that one sample is different than another sample. That's a differential instrument. So that needed a calibration. But if you could measure, if you could establish this to calibrate the air in a high pressure cylinder and then use that to calibrate that, then you scale up. So that was the overall concept. It worked very well. So this manometer has a series of columns of mercury here, but the truth is that this is redundancy. All it really needed was one of these large volumes back there. See the thing back there about this big as a glass flask back there? That held the original dry air sample. And you would measure the temperature by these thermometers in here. There's these amazing glass thermometers. You can read out to a hundredth of a degree. You measure the temperature, and you establish how big that volume is by filling it with water and weighing it. Okay, so he knew the volume, he knew the temperature, and he measured the pressure because he could look at the connection between that. There was a connection open initially between that chamber and this chamber over here. Sorry, a chamber that's connected to this mercury reservoir. We measure how high the mercury column was here, and then you can measure the pressure there. This would push down the mercury and cause this to pop. So you can measure the pressure with the mercury column height. Then you pump the air away. And he pumped the air away with pumps over here, and as the air is being pumped away, he freezes out the CO2 with liquid nitrogen. This is a trap you use for that. You pump all the air away, you close this off, then you warm this up, and now you pour a little bit of liquid nitrogen in this little thing right here, and then you open up the connection back so that the CO2 would be self-pumped, or would be cryogenically trapped, pulled back over because it condensed out over here inside this tube here. Then he pushed this mercury up to seal it off, and he would have captured the CO2 in this volume here. And then this mercury is all connected underneath, and so you can pump on it and push the levels up. So you basically control the levels. Phenomenal. So you push the mercury up until it comes to this pointer right here inside. And that pointer established a very particular volume, a volume of 4.127
0856
cc's.
That's one of the first things I had to
You went
do
to a lot of
to
trouble to
measure
figure out
it.
how big that was. Okay, that was important.
There was a lot of trouble.
Okay, so with that pushed up here, the same mercury, which is at a particular pressure at that height, will go all the way over to be the same pressure here, but then you have a vacuum on this side, the mercury would rise up to a vacuum. The difference in column height gave you the pressure over here as well. So again, you're measuring pressure volume temperature on the small sample. Then you pump it away. Okay, so how do you measure the height of this column? Get a ruler in here? Is that how you do it? How do you think you measure how do you think you measure the height of that?
It looks like he measured it with this.
There you go. Someone had their eyes open. He did it with this. So this is basically a short-range telescope, Cathodometer. It looks over here. It's all fixed angles. You look in here, and you dial this thing up or down until it's looking right at that thing, and then you dial it up to you're looking at the top of this level here. You have these little cards here so that you can very carefully see the top of the mercury column. They have little pointers to establish fixed levels. So the basic measurement was just this number right here. How high up or down that was going. But then you also had to measure temperatures.
So right now is 418 ppm? 418
No,
ppm?
that's just some arbitrary point on this dial here.
So what is the current level of CO2?
Oh, the current level of CO2 is about 400.
And where is that displayed?
Where's that displayed? I suppose it's sort of displayed right here, but that's not really up to date.
Okay, so what you said earlier was that your grandfather put this in, your father
Yeah.
put this in 50 years ago. It's connected to this side over here with the tubes, and so this really hasn't been touched for 50 years. So this is basically a very good 50-year calibrated snapshot of what's going on.
Yeah.
Because my question earlier was, is it the measuring that we're aware of the CO2, or is it the actual CO2? And you kind of answered that question.
This is how we know it was that level. Because he put this much trouble into getting it right.
Right, and that hasn't been touched.
There was actually a degree of overkill relative to what he really needed. He was just sort of like, I want to do it perfect.
Well,
He's
mention
a
that
perfectionist.
they rebuilt the building around this now.
This building
You
has
wouldn't
been,
let him move it.
This building has been completely refurbished. Then
No way,
Mr.
really?
Mr. Mulligan's
Steam ship, yeah.
Yes,
It goes in the basement and can't leave.
This is exactly that. They turned into a museum, right? Okay, you're living that. That's right here.
We're in
That's
another
cool.
building now across the way.
Yeah.
This is the only part of the original lab.
Try moving this big piece of glass.
Right.
It's not going to happen.
It's impossible.
It's impossible.
It's like juggling Christmas balls.
You break things.
No, you could cut those and
We cut the glass.
reestablish them. But even just
That's
moving this-
easy compared to moving.
But you have an area geographically located on the Earth that would sustain that temperature, because magnetic fields change everywhere you move. So if that moved, that
Well, this doesn't
mercury,
depend on magnetic fields. It does, however, depend on gravity.
Gravity,
Because-
gravitational
because
field, all that
the
changes.
relationship
This
between column height and
location-
pressure depends on local gravity.
That's
So
why he didn't want it
they
moved.
did have to know local gravity.
because he would lose all of his
People here
data.
at Scripps measure gravity.
So let's talk about this thing over here. So this
Mm-hmm.
is the analyzer used for making lots of measurements, and one of these was put in Mauna Loa, another one stayed here, and the one here was used to analyze air samples that were brought back to Scripps in glass flasks. And we should have a flask over here too.
I know.
That was
I-
that's part of this. By the way, this is just
Air
arriving.
samples from Hawaii were brought back here to
Yeah.
make.
Well,
Yeah.
in Hawaii there was an instrument.
Right.
There were also
On
samples
Mauna Loa.
collected there, so that was redundant kind of measurements.
Yeah.
But most of the other sites were just flasks.
We still bring flasks from all over the world.
For a short time, he had an analyzer running at the South Pole, and he also set up one in a place called Little America on the coast of Antarctica, not too far from Murdoch. But that one failed. They didn't get it. The pumps failed. So this analyzer, it's like you look under the hood of an old car. The thing that strikes you is how little is there. So a lot of empty space. The way this works is you measure the absorption of infrared light, and you can do CO2. So if you pass, and then as a light source, it simply uses a glowing bar, which is sort of hot red, so it emits a lot of near-infrared information. But it's, of course, emitting all these different wavelengths, and only a very few select wavelengths were actually absorbed by the CO2. So how did they make it sensitive? The way they made it sensitive was by having the detector actually be a cell of CO2 itself, pure CO2. Actually, CO2 and argon, but concentrated CO2. So the light would go through here and then go to this cell with the gas mixture in it. There's of course a window in there that let the infrared light through. And as the light went through, it would get heated up the wavelengths that would be absorbed by CO2 would be absorbed by the cell. So that cell was very specifically sensitive only to those wavelengths that CO2 would absorb. And then the whole thing was done differentially. You have two cells, okay? And then you have a chopper that alternates the light. So first you shoot this side, first you shoot that side. And these two cells back here are actually connected to a microphone. And so first you heat this one, then you heat that one. And you're doing this all at, I don't know, 40 hertz or something. So you're generating a 40 hertz sound wave. And you have a microphone that picks up the small pressure fluctuations. And it was set up in such a way with a null balance so that you actually got no signal when they had equal concentrations, and you only generated signal when they're out of balance. So it was quite sensitive at measuring the difference in concentration between one cell and another. And you simply pass air samples in here, and the reference cell usually just had a flowing gas, and it was not the reference cell is just an optical reference. So you would put samples in this cell, and then a standard in the same cell, and this would always have the same gas. And this way you develop a very careful calibration curve for this analyzer with gases that were calibrated with that. And that's the basis of getting measurements. Lots of measurements that were as well calibrated as that.
What is the frequency of the light? What frequency nanometer is the red light that absorbs CO2?
Well, I think the more relevant question
That
is
CO2 absorbs.
What temperature was the glow bar? But it was something. It was probably, I'm guessing it was something like 900 C. So it's a thermal source.
Really? 900C?
900, something like
But
that.
what
So
was the frequency of the
it's
light?
Still red. Well, it's a black body region at 900 C. So it's all those wavelengths at 900 C bar is. It's like the sun. What wavelength is the sun?
Your
The
dad
sun is a
was
black-
super, besides all this, he was super smart.
Well,
Because
Oh, yeah.
you know that. You know that. But that's
He didn't pass any of it on, but yeah.
that what you just explained right there is huge in that testing equipment. You have no idea.
Okay, well, let me explain one thing. He didn't build this. So I should say that this technology was developed by the Germans around World War II, and I think it was launched
One
by
for me.
the need to measure air on U-boats.
Okay.
But it's also been used in mines. So this had a lot of commercial. This was being rolled out as a commercial gas analyzing technology in the 1950s. It had never been used for measuring such low levels. 300 parts per million was kind of a small amount to detect. But he sort of worked the numbers and was bullish that it could work. And this company was willing to make 4 or 5 of these custom analyzers. They never built any more of them.
Wow.
But various other companies came in and built analyzers that sort of became the more standard workhorses of the community. He stuck with these, and we were still using this up until a year ago. And it took a lot of finagling to keep it going. Some of the tubes would burn out, and the microphones would flake.
Yeah, it's like an old TV.
The
You just had to
amplifier-
find tubes and
amplifier-
plug
there's
them
a
in
lot of
all
problem
the
with the
time.
amplifiers on the microphone. So a lot of it had to be re-engineered.
So what year did we put the first Siemens analyzer in at Mauna Loa? Was that 2003 or something
It
like
was more like 2005.
that? Okay. So one of these was running on Mauna Loa doing the Keeling curve until 2005, from 1958. That's pretty. I mean, you think about how many things in your house that you bought in 1958 would still be
My father
working.
was conservative.
He didn't want to change things. That's really for sure. Yeah. But it's pretty impressive that they would last that long.
The main, well, there's two. The modern. I should say that the techniques for measuring carbon dioxide today, now by a much larger community, involve a standards lab that does calibration, that disseminates tanks, and then the individuals measure almost entirely with infrared analyzers. Now there's a tendency to use laser methods rather than non-dispersive analyzers. But there's still a lot of these in use, and they're very rugged and simple.
1950s.
It's a great measurement principle, but it's not going away. Yeah, I'm doing similar work. I mean, basically, we have a lab that does all these things with modern stuff.
Well, no, we don't.
And we measure a whole
We
bunch
buy
of
the
things,
instruments, but we
isotopes,
do not
CO2,
believe in
levels,
them. Yeah, that's what they tell you to buy the instruments. How do you get to know it's gonna work?
Yeah.
The next year division.
In a way, it's
So-
really,
so when-
it's
when
really
does-
alarming
when-
how fast
When
it's
does the
going.
canary start? The canary start?
Yeah.
Well, I think it's already gasping. I mean, in some ways. I mean, certainly there's been a lot of big impacts already. So they're playing out in a time frame we don't necessarily appreciate how much things have changed.
Well, I
Yeah, I'm
think
sure we'll do something.
things are changing faster than maybe we thought they would. I always thought
Well,
climate
no,
change was going to
some
happen.
things are
in
faster, some
decades.
things are slower, but it's not like we have a real
So we
clear
need to grow a
crystal.
lot of algae.
Not, there's no
Well, there you
crystal
go.
ball as to what the future holds.
Stop the time, take it
Yeah.
easy.
I mean, it is clear that we haven't seen these kind of levels for millions of years.
Really?
Yeah, we did okay back then. Or should I say the planet? did okay.
Real.
Yeah.
I know, if you're not worried about
Marsupials?
human beings, you're good at
Well, actually, I'm not too worried about humans,
Yeah.
because we have a lot of ability to adapt.
That's a speed.
It doesn't mean that we won't kill each other off in the process in
Or
horrible
in
ways.
some other way, yeah.
Yeah. I mean, anyway. It's only one of many concerns for humanity's age, but it's up there on the list. Pretty high.
Thank you very much.
Thank you.
Very nice.
Thank you.
Thank you very much.
Thank you.
Yeah, you're very